Guys, Mr. Ground here, 8.1 Part 1, Simplifying Radicals and Pythagorean Theorem. In this video, we're going to talk about simplifying radicals. All right, so what do we mean when we simplify radicals? Well, let's first talk about what we mean when we talk about radicals. So we've all seen stuff like this: the square root of 4, the square root of 9, the square root of 16. You learn about this stuff in like elementary school, right? These are all perfect squares. We know that the square root of 4 is 2, we know that the square root of 9 is 3, and we know that the square root of 16 is 4. But why is that, right? Well, let's look at this in the opposite direction. Let's look at 3 squared, right? And what is that asking us? What it's asking us to do is solve this. 3 times 3 equals what, right? Equals blank. And we multiply the 3 together 2 times and we get 9, right? When we're looking at the square root of 9, now we're looking at this. 9 is the number, and we want to know what number it is that if we multiply it by itself, it equals 9. It results in 9. So it's really important to understand that like this product of two things equals the square. When we're taking the square root, we're trying to break it into these two things and think about what are these two things, right? Now, when we talk about simplifying radicals, we're usually, in this class, we're not going to be, we'll sometimes do perfect squares, but what we're really looking at are numbers that are not perfect squares. So things like the square root of 54, right? It's between 49 and 64 perfect squares, so it's somewhere between 7 and 8, right? The way that we're going to do this, we're going to write these numbers, we're going to reduce them and simplify them, get them into what's called simplest radical form. The first thing that we are going to do in order to do this is factor this number into its primes. We're going to make a factor tree. Now, when I make a factor tree, I like to think about what's the smallest number that I can divide this by. Well, it's an even number, so I can divide it by 2. So it goes to 2, and 54 divided by 2 is 27. These two numbers multiply to 54. That's how we're splitting this up, by dividing out small numbers. All right, 27. Now I can't split 2 anymore, right? Because it would just split to 2 and 1. There's no point to doing that. But 27, that's divisible by 3. So we can go 3 and 9. Now 3 doesn't divide by anything other than 3 and 1. But 9, that divides to 3 and 3. So I know that I've done the prime factorization. All of these numbers cannot, at the ends of the branches, none of them can be split any further. So that is all done. I'm looking for groups of 2, right? The square root means 2 things that multiply together to make that 9, right? So what I want to do when I'm using this strategy is find a group of 2 matching numbers and circle it. However many matching groups of 2 I can get, right? The next thing, anything that we circled, 3 times 3 is 9 and the square root of 9 is 3. Anything that we circle, we move to the outside of the radical. So that goes in front. Anything that's left, that's uncircled, now, the 27 and the 9, they don't count because we split those up. We're only looking at the numbers at the ends. Anything that's uncircled goes to the inside. And what do we do with those 2 numbers, right? If there's multiple numbers, we always multiply them together. Everything's a product. I broke this number apart by dividing. Now, when I put it back together, I have to multiply. So we've got 3 times the square root of that 2 and that 3. And if I simplify that now, 2 times 3 is equal to 6. All right, let's do a couple more examples. So our square root of 63. Now, it doesn't matter which number you start with. I personally like to start with the smallest number possible. So it's not divisible by 2, I know that, but it is divisible by 3. And if you have to get out your calculator and just start dividing by numbers, right, little numbers until you get something that results in a whole number, you can do that. All right, so 3 times 21 is 63. The 21 can split to 3 and 7. And now I have a group of 2 3s. That number goes to the outside. and then I've got 1 left on the inside. All right, so what does all of this stuff mean? Well, these two numbers are the exact same, right? They don't look the same. This we considered fully simplified because we can't reduce this 7 any further. But if you plugged in square root of 63 into your calculator and looked at the decimal number and 3 times square root of 7, it would be the exact same decimal number. These two things are equivalent forms of the same number. All right, 120. Now again, you might look at this and immediately want to divide it by 10. Totally fine. I'm going to divide it by 2, and this will be a little bit clearer why I do this in this one, because it's going to be a lot of factors. All right, so 120 divided by 2 is 60. We'll split it again to 2 and 30. We'll split it again to 2 and 15. And 15 is divisible by 3 to 3 and 5. All of these numbers are now in numerical order, and it makes a really neat, it makes the work much neater if you do it that way. It's not required, but it's my suggestion. Okay, looking for my groups of 2. I got 2 2s right there. I've got a single 2, a single 3, and a single 5, right? So what's going to happen, that 2 is going to move to the outside, and on the inside is going to be a 2 times a 3 times a 5. And my final answer is 2 times the square root of 2 times 3 times 5 is 30. Like that. All right, a little bit of a step up now. What happens when we multiply radicals together? Right? Now I've got 2 sort of examples here. This one, I'm going to use a strategy that's more universal. This one I'm going to take a little bit of a shortcut. I notice right away on this one that I've got a perfect square here. It's 3 root 12 times root 4, and the square root of 4 is equal to 2. So I can just start by replacing that with a 2. Right? Because square root of 4 is 2, why not just make it times 2? When you're multiplying these, the stuff on the outside multiplies together, the stuff on the inside multiplies together, but the stuff on the outside doesn't multiply with the stuff on the inside. So I am going to write this as 3 times 2, the stuff on the outside of the radical, and then the square root of 12 is on the inside. So that's 6 root 12. Now, am I done? Maybe, but I should probably check. That 12, if I can get any groups of 2 out of here, any matching groups of 2, I know I'm not done. So this is 2 and 6, and that goes to 2 and 3, so there's my group of 2, right? So I can simplify this a little bit further. I've got a 6 on the outside already. I'll multiply that with the 2 that's coming out, and then the 3 is what's left on the inside. And so my final answer, the 6 times 2 makes 12, so this is 12 root 3. All right, with our other one. Now this is a little more universal strategy. There's no perfect squares right away. So what I'm going to do is just multiply this, make it 1, and then simplify it. So the stuff on the outside can multiply together. The stuff on the inside can multiply together. But stuff on the outside and inside don't multiply together. So on the outside, it's going to be the 2 times 5, and on the inside, it's going to be the 30 times 3. That's going to give us 10 root 90. Now let's see if this simplifies. Can I get any groups of 2 out of here? All right, this splits into 2 and 45. The 45 splits to 3 and 15, and the 15 splits to 3 and 5. Now, if you did that in a different order, that's fine. You should end up with the same numbers, 2, 3, 3, and 5. They might just be a little more mixed up. There's my group of 2. So on the outside is going to be, we've got a 10 already. That 3 is going to join it. And then on the inside is this 2 and this 5. And we're left with 30 root 10.